Hey, hello everyone. I'm Sugan Anajima, and today I would like to talk about my research entitled Pilot Study on Semi-Automated Packaging by Applying Machine Learning Techniques. So, before I start my presentation, let me introduce myself a little bit. So my name is Sugan Anajima, and I'm a security researcher at NTT, which is the largest ISP in Japan. And my research interests include vulnerability discovery, reverse engineering, and IoT security. And I'm also a founder of Secret for Girls, which is the first female-emphatic community in Japan. And I'm also a regional review board of Black at Asia from 2018. And since I became a security researcher at NTT in 2013, I have presented at various security conferences and events such as Black at USA, ESA CCS, AIS3, and Positive Hack Days and SATCOM. So now, let's move on to today's agenda. Roughly speaking, this presentation is divided into two parts, part 1 and part 2. Both are stories about how we apply machine learning techniques with the goal of achieving semi-automated packaging. So, first of all, I would like to talk about the background of the research. Here, I will start with what is patch digging? Generally, when vulnerability is discovered, the software vendor fixes that vulnerable part and release the updated version of its user to its user. And patch digging is a technique to identify that patched vulnerable part by comparing the patch binary build and the unpatched binary build released from vendors. And by identifying the vulnerable part, and we identify the root cause of the vulnerability, and therefore it is sometimes used to create the wounded exploit code to attack the users who are slow to adopt the latest security updates. So this slide shows an example of applying patch digging on CVE 2006-4691. So CVE 2006-4691 is a static bulk-based buffer overflow vulnerability, which is found in the function called netp manager IPC connect inside the net-API32.dll. The left column shows the disassembled code and its pseudocode of the vulnerable part. And the right column shows the disassembled code and its pseudocode of the key part with some fix applied. So by comparing the two pseudocodes, we can easily find that the if statement, which checks the string size, in other words, the security checks, have been added to the patch version. And based on this change, we can confirm that this is indeed a vulnerable part. And moreover, we can determine the root cause of the vulnerability that can help create a wounded exploit for this vulnerability. So this is what patch digging looks like. So this patch digging technique has been well known since long ago among reverse engineers, and thus to support the diffing, various tools such as Primitive, TurboDiff, Diaspora, have been developed. However, although those fantastic tools greatly support analysis, patch digging is still a difficult task because it requires deep knowledge and experience. And therefore, to lower the bar, techniques that can support the patch digging are required. Based on this background, we believe that the first step is to develop a semi-automated patch digging tool. So next, I would like to introduce the previous work in this field. So with the same motivation as in our research, Jiang Wu developed a tool called Darwin Brim and presented it at Black Hat 2010. And after diffing the binary, this tool showed a candidate function that the security fix might have been applied. More specifically, Darwin Brim uses a heuristic pattern matching rule to identify and show the candidate function. For example, if the number of the comparison, the TMP instruction, increase in the third patch version function, Darren Grimm would add a predefined score called implication score. In this case, the TMP instruction, Darren Grimm will add 1 point to the function. So based on the total score, Darren Grimm displayed the function in order that are most likely to have had security fixes. However, unfortunately, there are only a few patterns, and moreover, these patterns are manually defined by the developer. Therefore, in this study, we conducted an experiment to investigate how we could apply machine learning to extract the security fix pattern automatically. So far, I've talked about the background and motivation of the research. Now, let's move on to the main part, the story that we challenged to extract security fix patterns using the machine learning algorithm. So generally, when fixing similar types of vulnerabilities, those fixes will also be similar. Here, I would like to show that using the fixes for the null pointer dereference vulnerability as an example. So null pointer dereference occurs when a program attempts to read or write to memory with a null pointer. When fixing the null pointer dereference, generally the security checks to determine whether the pointer is null or not will be ahead. For example, CB 2014-0198 and CB 2015-0288 are both null pointer dereference vulnerability found with OpenSSL. From this source code of the patch and non-patch version shown in the slide, we can see that in both cases, the if statement that checks whether the pointer is null or not has been added. And if the pointer is null, error handler is performed. So with this in mind, we try to extract a fix pattern using an unsupervised machine learning algorithm. So, next, about challenges. To extract security fix patterns from the binary executables, there are two main challenges. The first challenge is the assembly level changes mainly produced by the compiler optimization. More specifically, although the source code is the same, sometimes the compiler generates a different binary because of the various program optimization. So that could interfere with the pattern extraction. And the second challenge is that although a vendor says that this is a security fix, sometimes other fixes have been applied to the updated software. In the next few slides, I will give details about the challenges that are mainly related to the compiler optimization. So first, about the basic block reordering. So as you may know, basic block is a straight line code sequence with no branches in expecting the entry and no branches out expected at the exit. The order of the basic block is defined by compiler, and to reduce the number of the mispredicated branches in the final executable, sometimes the order may change. This slide shows an example of the basic reordering, which we found during the passage on TV 2015-1788. The left column shows the part of the assembly code inside the vulnerable function, and the right column shows the clean part of the patch version. So here, there are three basic blocks colored with green, violet, and orange. And you can see that originally the order of the basic block was green, violet, and orange. And however, the order has changed to green, orange, violet after the security key has been applied. So this is what basic block order looks like. So next, I would like to talk about the instruction reordering. The instruction reordering is conducted by the compiler in order to achieve efficient memory access this slide shows the example of instruction reordering, which I found in the program related to CB 2015 1798. The left column shows a part of assembly code inside a vulnerable function, and the right column shows the same part but compiled in the different compilation environment. You can see that the order for violent instruction is different between program 1 and program 2. And more specifically, originally the order was move, move, push, move, but the order has changed to push, move, move, move. So this is an instruction order. So next about operator changes. Here I would like to talk about the compiler optimization related to register allocation. So basically, compiler controls the register allocation, and to achieve efficient access to each variable, sometimes the located register may change. So this slide shows an example that we found in the program related to the CB 2008-5023. So the left column shows a part of assembly code inside a vulnerable function, and the right column shows the same part, but compiled in a different compilation environment. So as you can see, originally, the register for the valid colored part was EBX, but it has changed to R12D in program 2. So next, I would like to talk about the inline expansion and loop unrolling. First of all, inline expansion is one of the optimization techniques used by a compiler that replaces the function call set with the body of the call function. The first row of the table shows an example of inline expansion. The left column shows the original source code, and the middle column shows the disassembly binary on which the inline expansion is not applied. And lastly, the right column shows the disassembly binary in which the inline expansion is applied. So when you compare the right and left assembly code, you can see that the function called myFunc, which simply calls a printf function with given argument, is embedded inside the main function. In other words, the main function just calls the printf function directly with the given argument. So finally, about loop unrolling. So loop unrolling is another optimization technique. The second row of the table shows an example of a loop unrolling. So here, the original program calls a printf function 3 times using for loop. However, after the loop unrolling is applied, the program just calls a printf function 3 times without the loop. So far, I've talked about the challenges mainly related to compiler optimization. So next, about challenge number 2. So as I explained earlier, although vendors say this is a security fix, sometimes other fixes such as bug fixes, and refactoring and feature updates are included in the updated version of the software. So that's the challenge number 2. And next, I would like to talk about the overview of the experiment. So we collected 62 security fixes from OpenSSL version 1.1.1 as a dataset and conducted cluster analysis. So our goal here is to extract security fix patterns that could be used to support the semi-automated password. So next, about data collection method. As I mentioned earlier, we collected 62 security fixes data from OpenSSL 1.1.1. And more specifically, first we analyzed the GitHub commit log and the release notes of OpenSSL. and identify the commit ID of the patch version and the non-patch version related to all 62 CVEs found in OpenSSL 1.10.1. Then we define if this source code and identify the actual function that security fix has been called. And finally, we compile all the source code of the patch version and non-patch version and disassemble it, and then extract the assembly code from the final function. So here, I would like to talk about the feature extraction method. So first, we compare the function before and after patch and extracted an instruction that increased in the latter version. And then we normalize the extracted instruction. The reason for normalizing instruction is to make the instruction more accurate. So I will talk about the details of this step later in this presentation. And finally, we could calculate the number of words for each normalized instruction. So that's how we extracted the feature of the security fixes and created a feature vector. So now I would like to show how we normalize the instruction. Based on the normalization rule we have defined, we summarize and express the instructions that fall into similar categories by one normalized instruction. For example, branch instructions such as JNS, JLE, JME, and JGE are normalized as jump. In this research, we normalize the instruction that appeared in the dataset because it was difficult to make the normalization rule for every single instruction. So here, I would like to explain about what is cluster analysis. The cluster analysis, also known as clustering, is one of the unsupervised machine learning algorithms that divides data into groups that are meaningful or useful. But more specifically, clustering is the task of grouping a set of objects in such a way that objects in the same group, which is called a cluster, are more similar to each other than to those in other groups. For example, the left figure in this slide represents the dataset before clustering was applied. And by applying the clustering algorithm, we can automatically identify there are 3 groups in the dataset as shown in the figure on the right. So, broadly speaking, there are 2 types of clustering algorithms. First is the hierarchical clustering algorithm, and the second is non-hierarchical clustering algorithm. The first one, the hierarchical clustering algorithm, produces a classification in which small clusters of very similar data points are nested within larger clusters of less closely related data points. And the second one, the non-hierarchical clustering algorithm, generates a classification by simply partitioning the data. And here we selected the hierarchical clustering algorithm. So when applying the hierarchical clustering algorithm, we employ wire method to calculate the distance between the cluster. And moreover, we use the leading distance to calculate the distance between the data points. And next, I would like to talk about the level which we assign for each data. Here, we use CWE as a level. So CWE stands for Common Weakness Enumeration, and it is a list of the common weakness types maintained by Micro. And CWE gives a unique identifier called CWID to each type of vulnerability. For example, CWE 120 is CWID for the weakness type that is so-called classic buffer overflow vulnerability. And the latest version of the CWE is 3.4, and a total of 808 weaknesses are defined in this version. Furthermore, CWE organizes its wide variety of weaknesses in the hierarchical structure. The weakness type at higher level in the hierarchical structure is a more abstract and broad concept than the lower level weakness type. For example, CWE 120, the TWID from the passive upper overflow vulnerability is a child idea of CWE 190, which represent the buffer. Based on the Micro's official website, there are three types of hierarchical structure. First is called development concept, and second is called research concept, and third is called architectural concept. So here we use the root DWIDs of the structure called development concept as well to make the vulnerability type more abstract than the original DWID. For example, the root DWID for the CW 120 is CW19, which represents the data processing error. Moreover, the reason why we selected the development concept is that to that set of knowledge, it is the most standard one. For example, a Japanese vulnerability database called JPNIPDL also uses the development concept in its database. So this slide shows the overview result. The figure shown in this slide is a dendrogram which illustrates the arrangement of the cluster produced by the hierarchical clustering algorithm. So based on our detailed analysis, we found two clusters where most of the level in each cluster were the same. In other words, we found two clusters that were correctly clustered from the data set we used. So here I would like to show the details of cluster number 1. The table in the middle of the slide shows the level in the data that cluster 1 contains. As you can see, most of the level here are CWE19, which represent data processing error. In summary, based on the Google manual analysis, we found that most of the vulnerability in this cluster were related to the memory or value manipulation error, which was not initially expected by the developer. For example, vulnerabilities such as out-of-bound read, delete, and integer overflow were included in this cluster. Furthermore, when we analyzed the feature vector in this cluster, we found that all data in this cluster contains a certain number of comparison, branch, and arithmetic operation structures. So this means that we truly extracted the security fix patterns dramatically for CW19s using the clustering algorithm. So now I would like to show the details of one of the vulnerabilities in its fix included in cluster number 1. So CWE 2006-0797 is an integer overflow vulnerability found with a function called bn_x2bn, which converts the string containing the hexadecimal number to a big enough integer value. So more specifically, the integer overflow occurs in the variable called I in the bn_x2bn function. So this, as you can see, OpenSSL developer added a check to confirm that the integer value stored in the variable I is under the expected upper limit. Also, based on the further analysis, we determined that the other vulnerability in the cluster 1 will also fix like this. So that's why we got the pair of comparison branch arithmetic operation instruction as a security fix pattern at the binary level. So next, I would like to show the details of cluster number 2. The tables in the middle of the slide shows the values in the data in cluster 2. So as you can see, most of the values here are CW 254, which represents security features. In summary, based on our detailed manual analysis, most of the security fixes for the vulnerability in the cluster contain some sort of error handling function. And furthermore, when we analyze the feature vector in this cluster, we found that all data in this cluster contains a certain number of the data transfer, branch, and function related instructions. So here I would like to show the details of one of the vulnerability and its fix included in cluster 2. The CWE 2014-3470 is a null pointer to reference found in the function called SSL3 send-client key exchange. As you can see, the developer added two error handling functions called SSL3 send alert and SSL error with an error exit using a go-to statement. And also, based on the further analysis, we found that the other vulnerabilities in cluster 2 were also fixed like this. So that's why we got the pair of data transfer, branch, and function related instruction as our security fix patterns in binary. So, next, I would like to move on to the discussion. So first of all, I will start with why we found only two clusters that were successfully clustered. So this was because some vulnerabilities were found in multiple functions. And this is not a surprising result because sometimes similar functions contain same vulnerability due to various reasons such as source code reuse, etc. And because we use a number of occurrences of normalized instruction as a feature, we couldn't correctly cluster those kind of security fixes. And next, I would like to move on to how we could improve this. So this time, we only use instruction as a feature. Thus, one way to improve this is to include other features such as function operands. And another way is to improve this is to collect more security fixes to enrich the data set. For example, one idea is to use the vulnerability corpus generation tool such as Lava to collect more security fixes data. And furthermore, we could try using other machine learning techniques. And lastly, I would like to talk about how we could use the security fix patterns to achieve the semi-automated capacity. So we believe that if we calculate the similarity between the extracted security fix pattern and the increased instruction from the binary that the patch is applied to, we can show the candidate function that security fix might have been applied down the road. And here, we think that the security fix pattern could be extracted from the centroid, which means the representative data points of each cluster. So that's all for part 1. And now I would like to move on to part 2. So here I conducted an experiment to see whether or not it is possible to distinguish between the security fixes and other fixes by using machine learning. So first, I would like to talk about the overview of the experiment. So as same as the previous experiment, we targeted the OpenSSL 0.1 and collected 62 security fixes and 377 other fixes and extracted the feature data similar to previous experiment. And for the classification method, we use supervised linear classifier, which is called SVM with RDF curve. And we use 62 security fixes and cross-validation to 3 times. And cross-validation is one of the model validation techniques used to ensure that the model can perform acceptably in the real-world situation. More specifically, it shows how the model will perform on dataset not used in training. So here, I would like to briefly explain about what is SVM. So SVM stands for Support Vector Machine, and this is a machine learning method used for classification and regression data. So given a set of training example, each mark as belonging to one or the other of the 2 categories, and SVM training algorithm build a model that assign new example one category or the other. The figure on the slide goes through the overview of SVM. And this table shows the overall result of the experiment. So as I mentioned earlier, I conducted n-fold cross-validation 3 times to measure the quality of the model. And here I calculated the average accuracy, precision, recall, and export. So in summary, overall accuracy was 56% on average. The accuracy is a ratio of the number of correctly labeled fixes to the number of all fixes in the data. And unfortunately, 56% means that this model is not good enough to be used for determining whether a fix is a security fix or other fix. And next, I would like to dive into the details of this result. First of all, precision and recall for classifying security fixes were 61% and 41% respectively on average. In this case, precision is a ratio of the number of the correctly labeled security fixes to the number of all fixes labeled as a security fix by the program. Moreover, recall is a ratio of the number of correctly labeled security fixes to the number of security fixes in the data, to the number of all security fixes in the data. And furthermore, precision and recall for classifying other fixes were on average 55% and 73% respectively. And lastly, I would like to talk about how we can improve this. One idea is that we can use other metrics, such as psychometric complexity, to calculate the complexity of the program for the future vector. This is because, intuitively, the more function became complex, the more bugs would be produced. To conclude, I have summarized the choice on the slide. So first, I will talk about what classification is, and then point out the issue that without deep knowledge and experience, classification is still a difficult task. And then, based on the hypothesis that similar type of vulnerability will be fixed in a similar manner, we applied an supervised machine learning algorithm and extracted experience patterns with the goal of achieving semi-automated classification. And lastly, we also conducted an experiment to see if it is possible to distinguish between security fixes and other fixes.
Let's give her a round of applause. Come on.
It is possible to distinguish between experiences. We believe that the insights provided in this talk will help other researchers who will be conducting similar research in the future. Okay, so the original paper of this research can be downloaded from the URL shown in the slide. So I would like to acknowledge the co-authors of the paper, Ren Kimura and Yuhei Koya, still have like 5 minutes. So I would like to introduce my other research and activities a little bit. And first of all, I would like to introduce my research related to IoT security, which is presented in this year's AJ6S. So this is a study about vulnerability disclosure and patch release behavior, which targets consumer IoT devices. So during the research, we revealed 3 significant one-day risks related to IoT devices. For example, we found that regional subsidiaries of some IoT vendors, would often release the patch against the same vulnerability on different dates. For example, Diffing in Germany released a patch for CP 2017 7852 in November 2015. However, unfortunately, the Diffing in the US released the same patch in July 2016. So this is 244 days after the Diffing in Germany patch release. So during these 244 days, attacker can easily create a one exploit and exploit the other country, in this case, the US. So in the paper, we get this risk geographical arbitrage. So for more details in the original paper, the PDF file could be downloaded from the URL shown in the slide. And so far I've talked about my research, and I still have a little bit of time. So next I would like to talk about my activities about Diffing for growth. So as I explained at the self-introduction slide, Diffing for growth is the first female interfaith community in Japan, which was established in 2014. And Diffing for growth holds women-only CTF workshop 2 to 3 times per year, and up to now we have held a total of 14 workshops, and more than 700 women have participated in the workshop. So if you are interested in Diffing for growth, please feel free to contact me or access our official website or Twitter. So that's all for today. Thank you very much for listening. If you have any questions,